All right, so looking at non-constant acceleration, you'll see this marble goes down this curved ramp, and for the first 2 seconds, it's almost constant. Almost. The velocity is definitely picking up steam right there. And then as it goes further down, it's going to stop increasing in velocity. So the velocity is almost going to hit its maximum right about here. Or it's definitely going to hit its maximum right about here. So that means the acceleration is getting smaller and smaller and smaller as we go. Because remember, acceleration is the change in velocity per unit time. Almost constant slope. And what's the slope of velocity versus time? The slope of velocity versus time is acceleration. Last second, there's much less steepness happening. Acceleration, or the slope, decreases as the steepness decreases. So acceleration is the change in velocity over time. That means that a ramp with a curve gives an object changing acceleration. You can figure out a lot of things with changing acceleration. A lot of times we're going to look at using energy. We can easily solve this with energy if we wanted to figure out how fast it was going at the end just by using our conservation of energy, knowing at the very top all of our energy has to equal all of our energy at the end if it's a closed system. So we would say the gravitational potential energy right here equals the kinetic energy down here, and we could solve for speed. However, if we wanted to use something other than energy, we would need to use calculus, which learning calculus for physics is not that big of a deal, and I believe that it helps tremendously in understanding. So it's not too late. Go back to Unit 1, look up derivative, and you'll see some tricks on how to do this, and there'll be some calculus practice. Free fall. Special constant acceleration. A special type of constant acceleration is called free fall. Definition of free fall is the motion of an object where the only force acting on the object is the weight force. That means that the object touches no surface, so there's no normal and no friction, and the object touches no rope, springs, or humans, which are tension, elastic, and applied force respectively. Air resistance on the object are so small that we are able to ignore them. You'll see that in the wording air resistance is negligible, or air resistance can be ignored. If two different mass objects are dropped from rest at the same time, the heavier object reaches the ground first. Misconception, no, that's not right. This is interesting because this is what the world always thought. If you have more mass, then that object wants to get back to the center of the earth more than the lighter object. And that was always thought to be true. And then finally, Galileo comes by and, as legend has it, drops a cannon and a feather from the Leaning Tower of Pisa, drops them, and they both hit the ground at the same time. Obviously, that's not realistic. It would have to be a cannon, if you want to use a cannonball, and then a smaller ball, and drop them at the same exact time. And you would see that because they're round, air resistance can be negligible because the air is going to come right off of it. And you would see that the two objects reach the ground at the same time. So Mr. Wright says objects are in free fall, have the same acceleration, so the two objects drop together, fall at the same time. Galileo showed this when he allegedly dropped a heavy metal ball and a light metal ball at the same time from the Leaning Tower of Pisa. Both objects fell together, even though they were different masses. Fun fact, I did not know this slide was here, so forgive that story before. But there it is. Misconception says, but if I drop a dense ball and a feather at the same time, the ball goes straight to the ground and the feather takes a lot of time to reach the floor. Doesn't matter. That's because the feather is not in free fall. It has a significant amount of air resistance acting on it. Astronauts on the moon, where there is no air, repeated Galileo's experiment, 1969, with a hammer and a feather. They found that both fell together. So it's a falcon feather and a hammer. This is the hammer in his right hand, and in his left hand is the feather, and you see that they hit the ground at the same time. I know the graininess of the video is not great by today's standards, but you can still see they're hitting the ground at the same time. The acceleration of all free-falling objects on the Earth, or near the surface of the Earth, is 9.8 meters per second squared. This is the same number we use for the gravitational field of Earth, which is 9.8 newtons per kilogram. We will find out later that newtons per kilogram and meters per second squared are the same thing. It's because of Newton's second law, F equals ma. That's not exactly Newton's second law, but that's all right. Free fall only occurs when the object is moving downward towards the floor, right? No. An object can be moving upwards or downwards or sideways or at an angle if it's in free fall, as long as the only force acting on the object is the weight force. So things launched through the air, we call those projectiles. Projectiles moving at any point along their trajectory or path, they're experiencing free fall also. Ball is not in free fall. We're looking at the height versus time, velocity versus time, and if I will get out of the way, we can see the acceleration versus time. So you can see these blips happening on the acceleration versus time. That indicates that there is some huge amount of acceleration happening every time the balls hit the ground, which has to be true because those balls are changing direction, and the only way to change direction is to stop, and the only way to stop is to have an acceleration in the opposite direction of your velocity. There's no place for me to go. You'll have to read that. Yellow arrow is a ball's velocity, and the red arrow is a ball's acceleration. Note that the ball is in free fall as long as the ball is not touching the floor. So when it's not touching the floor, as it's falling down, the acceleration is in the same direction, so it's speeding up. And that's the only force acting on it, so it's got to be in what we call free fall. When the ball does not touch the floor, the only force acting on it is the weight force. When the ball does touch the floor, the ball has a normal force put on it, right? Because the floor is a surface, and the normal force is normal to the surface, perpendicular to the surface. When the ball strikes the floor, the normal force is much greater than the ball's weight. This is because the normal force needs to stop the ball's downward motion and start the ball's upward motion after the bounce. So the upward normal force has to be stronger than the weight to first stop the downward motion and then start the upward motion. The strong normal force is what injures you when you fall and you strike the ground. Each individual free fall motion is a downward opening, a parabola on a position versus time graph. Each individual free fall motion is a downward sloping line on a velocity versus time graph. The slope is 9.8 meters per second squared for free